Let's take a look at section 5.7, which is on inverse trig functions. So you may or may not remember this from pre-calculus, and we didn't get a chance to go over inverses in this class very often or very much. So what we're going to do, I just want to remind you of what it means to have an inverse when you look at it graphically. There's some theory behind this, and it goes back to the definition of an inverse, but basically the rule of thumb is it's got to be 1-to-1, which means it has to pass, if you're looking at the graph of it, has to pass what's called the horizontal line test. You don't have to remember this, so don't worry too much about it. I just want you to kind of see where this is coming from. So the horizontal line test works the same way as the vertical line test. We draw a line horizontally, and if it hits the graph in more than one location, then it does not have an inverse. The graph you're looking at does not have an inverse. So if you think about the basic sine curve, you can see right away it fails the horizontal line test in multiple places. Because remember, the sine wave, it keeps on going in both directions. So somewhere along the line, we came up with a need for coming up with inverse functions of these trigonometric functions, and we needed to have a way to work with their inverses, even though they don't pass the horizontal line test. So what we decided is we would restrict the function on a particular interval so that it would pass the horizontal line test. So for the sine function, what we do is we take the interval from x equals negative pi over 2 to positive pi over 2. So if I take the same graph and I zoom in, negative pi over 2 is over here at negative 1 is the y value. Positive pi over 2 is up here, and the y value is positive 1. Kind of a zoomed in superimposed image of that is right here. So from negative pi over 2 to pi over 2, here's the same function. We've just kind of zoomed in. You can see that this now passes the horizontal line test, which means that now this has an inverse for it. And so that's what we're going to be working with. This is going to give us our inverse trig function, or inverse sine function, or also known as the arcsine function. Same thing. There's two different types of notations we're going to use for these. And all of the 6 trig functions can be restricted in a similar way so that each one will have an inverse. So let's go through the 6 trig functions and then what the domain and range are for each one. And let me back up for just a second. Another property of inverses to keep in mind, this actually is very important, so try to remember this. The domain and range are all swapped. So if I look at the original sine function, and the domain for the original sine function that I'm going to work with is from negative pi over 2 to positive pi over 2, this will become the range, because the domain and range are swapped, this will become the range for the inverse sine function, or the arcsine function. Let me show you what I mean. So take the arcsine function. The domain is going to be from negative 1 to 1. And the reason is, let me go back really quickly to the graph. What was the range for the original sine function? The range was negative 1 to 1. So that becomes the domain for my inverse function. And then the range for my inverse function becomes the domain for the original sine function. This range is really what you want to remember. These restrictions are very important when we're working with these. So these ranges are what you're going to want to remember. The arc cosine function. The domain is the same. It goes from negative 1 to 1, and that's because that's the range for the original cosine function. The range for the arc cosine function, in other words, what we restrict it to so that the graph of the cosine would have passed the horizontal line test, is 0 to pi. Now, as we go through these, for these two in particular, I want you to think about what quadrants on the unit circle these would put us in. So 0 to pi is maybe a little bit easier to think about. 0 to pi would be from the first quadrant all the way around to the second quadrant. So my answers, when I work with an arc cosine function, my output values should be either in quadrant 1 or quadrant 2 because of this specific range. From negative pi over 2 to pi over 2 for the arcsine function, that includes the first quadrant and the fourth quadrant going backwards. So the first and the fourth quadrant are going to be where I'm restricted to for the arcsine function. Arctan, the domain is all real numbers, and the range for arctan is the same as the range for arcsine with the exception of the endpoints. It does not include those because tangent's not defined there. Arc cotangent, domain is all real numbers. The range is the same as for arc cosine, again, except at the endpoints because cotangent is not defined at those locations. Arcsecant is not quite as common, and arccosecant, we may see them from time to time, but we're not going to do as much with those. Really, sine, cosine, and tangent are the three we're going to work most with. But here's the information for arcsecant and arccosecant. So what kind of a question might we be asked? So if I said evaluate the arcsine of -1/2. So what this really is saying is what value or what angle, let me say that again, what angle on the unit circle has a sine value of -1/2 and is in this interval. So the sine values or the locations, I should say, the angles where sine equals +1/2 are your pi/6 values. But we want to go backwards into the fourth quadrant, so that gives us -pi/6 for that one. Let's do arc cosine of 0. So what that means is between 0 and pi, at what angle does cosine equal 0? So think about your unit circle between 0 and pi. Where does cosine equal 0? Cosine equals 0 in two locations, but the one we're interested in is in this interval 0 to pi. So from the first to the second quadrant, that would be at pi/2. Solve for x. So if we have arctangent of 2x minus 3 equals pi/4, we can take the tangent of both sides, and what that effectively does, it undoes the arctangent on the left side, and that leaves me with 2x minus 3 on the left side equals the tangent of pi/4, which is 1. Tangent of pi/4, first quadrant, pi/4 tangent values are 1. And so solve that equation, you get x equals 2. Okay, let's give this one a try. It says, given y equals arcsine. And by the way, this is another notation for inverse sine function. You may have seen this in pre-calc. We can either use arcsine or sine with this little -1. It's the exact same thing. They just use two different notations. It says find the cosine of y. So what you want to remember is y is an angle. So I'm asking for the cosine of angle y. And y is the angle whose sine value is equal to x. And we can think of that as x/1. So what we're going to do is we're going to draw a little triangle. And what the given information tells us is what I just said, that the sine of that angle y is equal to x. Where am I getting x? That's the argument right here. So if I draw a picture, I'm going to label one of the angles y. So I'm just using a generic triangle here, none of the quadrants right now. I'm labeling one of the angles y. I know that sine of that angle y is equal to x/1. So sine SOHCAHTOA. Remember, sine is opposite over hypotenuse. And so if I use the Pythagorean theorem, and we can go over this again in class, but if I use the Pythagorean theorem, this adjacent side is going to be the square root of 1 minus x squared. So what was my question? My question was find the cosine of angle y. Well, now I have my triangle labeled. So to get the cosine of angle y, SOHCAHTOA, cosine would be the adjacent over the hypotenuse. And so that would give me the radical over 1. So my final answer is just the square root of 1 minus x squared. Here's another one. Given that y is equal to the inverse secant of radical 5/2, find the tangent of y. Remember, y is the angle. So we're looking for a triangle where the secant of that angle y is equal to the square root of 5/2. Secant is the reciprocal of cosine. So cosine is adjacent over hypotenuse. Hypotenuse over adjacent would be the secant value. So radical 5 is the hypotenuse, 2 is the adjacent. Using Pythagorean theorem, we would get 1 is the opposite side. And so what was my question? I wanted to know the tangent of that angle y. So tangent is opposite over adjacent, which is 1/2. These triangle problems shouldn't be too bad if you draw a picture. I like them because if you don't remember all your unit circle values, it's not quite as bad. You can just draw a picture and figure them out as you go. All right, let's get into some of the calculus now. So the derivatives for your inverse trig functions. Just a quick background on where this formula comes from. It says, start with the composition identity. Sine of inverse sine is equal to x, and that should make sense because inverses undo each other, like we saw a few minutes ago with that arctangent equation. So this would just leave me with x. Take the derivative using a chain rule. So the derivative of the outer would be cosine, evaluated at the inner, which is the inverse sine, times the derivative of the inverse sine, which I don't know yet. So I'm going to leave that d dx of inverse sine. Now, my goal here is to derive a formula for the derivative of the inverse sine. So this cosine of arcsine expression, I'm going to divide it to get it to the other side. And now I'm going to draw a little triangle to come up with an expression for this denominator. So this is the angle whose sine value is equal to x over 1. So I'm calling it angle y just to give me something to call the angle. So if this is angle y, the opposite is x, the hypotenuse is 1, the adjacent side is this radical. So the cosine of angle y would be the adjacent over the hypotenuse, which would be the square root of 1 minus x squared over 1. That becomes your denominator. So my expression is 1 divided by the square root of 1 minus x squared. If this didn't make complete sense to you, not a problem. Don't worry about it. This is what I want you to put in your notes. The derivative of the inverse sine function is 1 over the square root of 1 minus x squared. That's what we're going to be working with. Inverse cosine, I'm going to skip the details here and just get to it, and I'll show you that the derivative for the inverse cosine function is the negative of 1 divided by the square root of 1 minus x squared. So similar to the one for inverse sine, except it's negative. All right. Let's go through the others. So here's kind of what we've done so far. There's the inverse sine derivative. Here's the inverse tangent derivative. It's 1 divided by 1 plus x squared. Here's the inverse secant derivative. This one comes up from time to time. 1 divided by the absolute value of x times the square root of 1 minus x squared. Now the other three are the same except they're negatives. So cosine, derivative inverse cosine is the negative of that same one you used for inverse sine. Derivative of cotangent is the same as tangent except it's negative. The derivative of cosecant is the same as secant except it's negative. Most of the time when we work with these, we're going to be using a chain rule. Otherwise, it's just the formula itself. We gotta have a little more to it than that. So most of the time when we do use these, we're going to be using the chain rule. So if I want the derivative of arcsine of 2x, the derivative of the outer function, which is arcsine, evaluated at the inner, times the derivative of the inner function. So we have 1 over the square root of 1 minus, but evaluated at the inner, which is 2x squared, of course, times the derivative of 2x, which is 2. Clean it up a little bit, we get this. Let's try another one, the derivative of arctangent of 3x. Look at your notes. What was the formula for the derivative of arctangent? This is a chain rule again, where arctangent is the outer function, 3x is the inner function. So it's the derivative of the outer, evaluated at the inner, times the derivative of the inner. Cleaned up a little bit, we get this. How about this one? The derivative of arcsine of the square root of x. So pause the video and go ahead and try it using a chain rule. So we have 1 over the square root of 1 minus the inner function squared times the derivative of the inner function. Clean that up a little bit. Let's put the 2 and the x to the 1/2 in the denominator. You can leave it like this. I'd be okay with this answer. If we distribute the radical through, we get the square root of x minus x squared under the radical. How about this one? We have the derivative of arcsecant of e to the 2x. So arcsecant is the outer function, e to the 2x is the inner function. So the derivative of the outer, there's your arcsecant formula, evaluated at the inner, which is e to the 2x. Now, the derivative of the inner, e to the 2x, is another chain rule. Make sure you see that. The derivative of the outer, which is e, evaluated at the inner, which is 2x, times the derivative of the inner, which is 2. Cleaned up a little bit, we get this. Make sure you see what happened here. This e to the 2x up here canceled with this e to the 2x down here. This 2 went into the numerator. E to the 2x squared, you multiply those exponents together to simplify, and that's where the 4x comes from. All right, let's try this one. We've got the derivative of inverse sine x plus x times the square root of 1 minus x squared. So the derivative inverse sine x, that's just the formula, no chain rule involved. The second half of this requires a product rule with a chain rule for the second half. So let me give you a minute. I want you to pause the video and I want you to try this first and then come back. So the derivative inverse sine is 1 over the square root of 1 minus x squared plus the derivative of the first, which is 1, times the second recopied, plus the derivative of the second, which is a chain rule in itself, times the first recopied. Clean it up a little bit. I'm going to cross those 2's out. I'm going to make that x times x right here. These x's together gives me x squared. And I'm going to move this radical to the denominator so that it's a positive exponent. You could leave it as a 1/2 or make it a radical again. That's fine. This answer is perfectly fine. I would stop here. I might have gone a little further in the PowerPoint and look at this. I got a common denominator. Forget all that. You don't need to go to all that trouble. This answer back here would have been just fine, as long as you get rid of the negative exponents and cross out anything that reduces.